All right, good afternoon, everyone. My name is Brandon Dotson from UCF. Nothing better than after lunch than to talk about some moon dirt. So before we get into it, I'd like to thank some of the co-authors who are in the audience here, Parks Easter, Jared Longfox, of course, my advisor, Dan Britt, and committee member Addie Dev for all the help on this. So before we jump into it, let's start with a few definitions to make sure we're all talking the same language here. So shear strength, what is it? It's a material property, and it really represents, especially for a granular material, the amount of resistant force that you can have to a shearing load. There's also cohesion, which is also a material property. And that's really the same thing, how sticky the material is to itself without a normal load applied. And they're related by that equation in the top right, which is the Moore-Coulomb failure criteria, which is really the shearing force is related to the normal force, internal angle, and then cohesion. And then for those who aren't like geotechnical people like myself, the little chart in the bottom, you can see the x-axis is normal load, y-axis is shear. And so that makes a line, right? And so that y-intercept is cohesion. I will point out too that there are a lot of papers that look at the nonlinear effects. So at low gravities or very low normal loads that you do get a nonlinear effect, and that's related to really the tensile strength of the material. We're not including that here because that's a little bit more complicated. Future studies. Okay, next slide, please. This is not clicking. Okay, so why do we care about these? So really, if you're driving on, walking on, landing on, building anything with regolith, or you're trying to dig it, shear strength and cohesion are important for that. So I've just thrown up a few real world examples of where this has bitten some missions. So of course, the Spirit rover on Mars got stuck in some low cohesion material on the surface, and that ultimately ended that mission because it couldn't recharge. The InSight robotic arm, of course, the heat probe on there, there was some issues with that actually digging into the surface of Mars, and that was due to low cohesion. And then Apollo 12, the lunar module, which you see on the top ridge there, actually landed next to Surveyor 3. And in the process, kicked up a bunch of dust because the exhaust velocity exceeded the shear strength of the material and sandblasted the Surveyor instrument. And some of that was brought back to Earth and examined. Next slide, please. Okay, so why do I personally care about this? So my research focuses on plume surface interactions, or that last bit I was talking about, namely looking at small subscale tests in the lab here using Regolith simulants. And so really my work is focusing on how does cohesion, density, and shear strength factor into crater formation and viscous erosion. Next slide, please. Okay, so discuss methods real quick. So essentially, we went in and measured a bunch of different densities, and I'll show that data here in a minute. Density was controlled using vibration, not compaction. Looked at particle shapes and sizes. I'm really just going to talk about the size distributions today. So one of the examples you see here, for those, again, who aren't geotechnical people, typically particle size distributions look like that sort of S-shaped curve there on the right. And there's different parameters that people use to describe those, be it a D50 coefficient or D10 or D90. Trying a new approach, which is to look at the incremental particle size distribution, or that blue plot in the bottom. So essentially fit that with a Gaussian and looked at the full width half max of that and related that to other properties. Next slide, please. So this actual setup, it's really pretty complex here. It's a box with some regolith simulant in it, and then we shear it with different normal loads on it. And that's used to produce that same linear relationship I showed on the earlier slides. And you can see some of that data on the right for LHS at 1.6 grams per cubic centimeter. And so again, that y-axis is where you pull out cohesion. Next slide, please. So with that, Exolith has a number of different simulants, including Lunar Highlands, Lunar Mare, some dust samples that are less than 40 microns, a whole bunch of Martian ones, some with agglutinates, and essentially went through all of those, plus some controls being just glass beads of different sizes, and repeated this test at a number of different densities to look at cohesion and shear strength. Next slide. Okay, so that last plot I was just showing you of a single line, that's literally one point on this diagram. So right here, I'm just showing LHS and what that looks like. So on the x-axis, you have density or bulk density, so including porosity. And on the y-axis is cohesion. I'm just going to build this for you because it gets a little busy. So next, please. So here's all of the lunar ones, and you can see that that's actually like that same exponential relationship is there for all the different types. And of note, even some of the samples that had like agglutinates in it, we really didn't see a huge change in cohesion with density. Next slide, please. Here's the Martian ones overlaid. Again, very similar. So you can see there's some trends that sort of fall out of this. Next, please. The glass beads, not as exciting. You can't get to as high of ranges of densities. That makes sense from a packing ratio standpoint. Next slide. And then really throwing on here some published numbers that you'll find for some of the simulants in literature. And so the big thing to note here is that, next slide, is that cohesion increases exponentially with density is what we found. And so when you look in the literature and you see a bunch of numbers thrown out, sometimes they're on the order of a couple hundred PA, and sometimes they're like 1,000 or 2,000. And this is likely the reason why, is because it depends on density. Next, please. So big table full of numbers here after lunch to put you to sleep, but essentially just pointing out that we fit all of these with an exponential. We've got the curve fits in here, and the R-squareds are all around 0.9. Next, please. So really try to take a look at those fit parameters and see if there's any relationships between that and that full width half max value that I showed before. And if you could build it for me, please. Essentially what that looks like is those fit parameters do depend largely on uncompressed bulk density and the particle size distribution, namely that full width half max. And so that relationship we've used to feed this model for cohesion. And what does that mean? Next, please. This is really rough without the builds, man. I'm sorry. So what does that mean? It means if you're not using specifically that make of LHS1 or LMS or that particular simulant, these equations help derive a general approach. So if you know what the particle size distribution is and you know what the uncompressed bulk density is, you can get you in the ballpark of what that cohesion would be. Next, please. Okay, same thing with that internal angle. You can see there's a bit more noise in this, and this does need a little bit more refining to kind of look at. And if you can build it for me. So really using a fat marker here is how we address this. So really, if you look at some of the data points, you'll see that internal angle will decrease for certain simulants. When you go to higher densities, sometimes it increases. So we're using this very fat marker here to write an equation. Next, please. So yeah, really the idea here is that internal angle also varies with density. Next. Okay, so putting this all together, you probably realize that this is actually a 3D fit. And this is not like a normal way that you see this data presented. We think it's very helpful because it kind of gives you an idea of the trends that you see between normal force, shear strength, and of course, density. And so to highlight that on the next slide, we'll show you an example of how we use that display to kind of help flesh out some other attributes. So in this case, we looked at LHS1D, which is the dusty version of LHS, made that whole 3D plot, and then basically baked the LHS to get all the absorbed atmospheric water out for 24 hours and reran those tests with that baked sample. And so essentially, if you subtract those two surfaces, you can see what the difference is in terms of shear strength that the water is causing the absorbed atmospheric water. And that's the chart on the right. And so really what you see there is that it's not uniform. So for lower densities, the particles are far enough away that the water doesn't really interact that much with them. At higher densities, they're so compact that, again, it doesn't really do much, but it's that sweet spot in the middle where you can see up to 15% increase in shear strength. Just from having absorbed atmospheric water. Next slide, please. So really that means, yeah, there's a non-uniform effect there. And really the so what is if you're using these materials in atmosphere on Earth to simulate things on the moon, building things on the moon, the properties are not going to be the same. And it's not uniform. And it depends a lot on density. Next slide, please. So in conclusion, we've put together using empirical data some generalized equations for cohesion and shear strength. Some of the key findings is that cohesion varies greatly with bulk density, as does internal angle, and then absorbed atmospheric water is another important consideration. And so if you're building stuff on Earth, if you're testing stuff on Earth, you're testing instruments, it's important to include these things as considerations before trying to send it to the moon or other bodies. All right, with that, any questions?
Yeah, thank you. That's very on time. We can have one quick question.
We will take more questions in discussion.
Hello, Connor Westcott, Florida Space Institute. So you mentioned that the water absorption non-uniformly impacts the cohesion. Have you considered, once removing all the atmospheric water, introducing like icy dust? If we're going to go to the permanently shattered regions and there's, thought to be surface ice with this dust, it's kind of important to know how that's going to impact when we try to start traversing that.
Yeah, absolutely. So this is really just the first step in this. So really the next idea is to look at this in a vacuum to see like how much that changes. And yeah, so icy simulant as well would be something to look at and how that affects cohesion and shear strength for sure. Yeah.
Thank you.
Thank
Okay,
you. Let's
thank you.
thank our speakers. And